And I'm convinced that if there's something real and ATLAS and CMS do the full run-through analysis, we will see something at the 5 sigma level. This should be there.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a fantastic week and have a brilliant weekend in store. My apologies for being a little bit quiet over the last couple of weeks. I've had a lot of tutoring to do and also had my first holiday in a long, long time. So we are back on the horse now. Now, this week, we're going to be discussing a very intriguing possibility. The possibility that there's more than one Higgs boson. Many people think that the discovery of the Higgs boson in 2012 was a one and done. Higgs et al. Predicted the existence of the particle in the 1960s, and it was finally discovered 50 years later. Surely that's largely end of story. However, things may not be so cut and dried. Numerous theoretical models predict so-called extended Higgs sectors and suggest that there may not only be one Higgs boson, but several. Such hypotheses and the existence of additional Higgs bosons could help us to address massive open questions in physics. The origin of electroweak symmetry breaking and the masses of fundamental particles, the excess of matter over antimatter in our universe, and even the origin of dark matter. Extended Higgs sectors are a rich field of theoretical study, and experimental physicists at the LHC are actively searching for signals of new particles, including potential additional Higgs bosons that may have been overlooked to date. Now, some theorists believe that we may finally be seeing hints in the LHC data that the Higgs boson that we know is part of a wider family. To help me dig into this intriguing possibility that there could be more Higgs bosons just waiting to be discovered at the Large Hadron Collider, I'm joined by a phenomenal special guest, Professor Sven Heinemeyer. Professor Heinemeyer is a theoretical physicist at the Instituto de Físico de Cantabria in Santander, Spain. His research interests include using the Higgs boson at 125 GeV as a probe of the Standard Model and beyond Standard Model physics, phenomenological predictions for current and future colliders in the Standard Model and beyond Standard Model models, calculating low energy and electroweak precision observables as tests of the Standard Model and beyond Standard Model physics, and much, much more. Recently, his work has focused on the intriguing possibility that we may be on the cusp of discovering additional new Higgs bosons at the LHC. So I couldn't hope for a better guest to help me dig into the intriguing possibility that there's more than one Higgs boson. So Sven, first up, for the people who are watching who might not know too much about the Higgs boson, surely there's only one Higgs boson. The one we found, it appears to behave pretty well. It appears to couple to things proportional to their mass. It validates our hypothesis for where and how fundamental particles acquire their mass. How could there be more? Why are we needing these extra ones?
Well, it's true that we have found one Higgs boson, and it behaves within the experimental and theoretical uncertainties as predicted by the Standard Model. But these uncertainties are at the level of around at least 10%, depending on what one is looking at. And this is indicated by these error bars that one can see, for example, better on the lower one, on the lower line. I mean, there's this lower box, there you can see the error bars a bit better because the other scale is logarithmic.
Yes, that's right, And I think there's some, that if I found another plot as well, which I might add in later, there's the ones for the quarks, which are very, very large because we haven't had the precision to be able to...
yes, exactly. For the C quark or so, it's much larger still. And it is exactly in this range of this 10% or so where one would expect that new physics comes in. So I'm not disappointed by that. There are many models that also naturally give you exactly the same couplings within a few percent of the Standard Model. So we still need much more precision to be precise there. But you ask, why should there be more Higgs bosons? And the reason is that models with extended Higgs sectors, meaning more Higgs bosons, can explain some of the shortcomings of the Standard Model, or candidates to explain those. And this naturally often leads to models where we have more than one Higgs boson.
So in terms of looking at this, these results that we're seeing for the standard model Higgs that we found, or what we believe to be the standard model Higgs.
You shouldn't call it the standard model Higgs from the start. If it's the standard model Higgs, yeah.
I'm falling into the trap.
At the LHC.
Yeah.
Yeah.
The Higgs boson that we found at the LHC, leaves room, despite the behavior that we observe, leaves room for the possibility that there's other Higgs candidates in an extended
definitely. And there are good arguments why there should be more Higgs bosons. But I'm sure we'll come to this.
We're definitely going to come on to that. So there is still room for these additional Higgs to be hiding, despite the discoveries that we have made. That's the first point to make. Definitely. So what kind of models are we talking about here, Sven? So 2 Higgs, 3 Higgs, 4 Higgs, n Higgs, where n is a big number. Yes. What are we talking about here?
Well, I don't want to go to too many technical details.
Okay.
In the standard model, it's correct that we have 1 Higgs boson, but let's say originally how the Higgs mechanism is constructed, we start out with 4 components of the field, and 3 of them are used to give mass to the gauge bosons, the massive gauge bosons of the standard model, the Z, the W plus, and the W minus. So I always say one of the most important calculations in the standard model is 4 minus 3 equals 1.
Yeah.
Yeah. So we start off with 4 components, 3 are needed to go somewhere else, and then 1 remains, which is the Higgs that we've seen.
Yeah.
Now, and then one can add more structure to the Higgs sector. This can be another 4-component object. This can be a 1-component or a 2-component object. And then these add either 1 or 2 or 4 more physical Higgs bosons to the model, to the spectrum that one can expect. And this then depends on what you want to achieve with these extended Higgs sectors. Whether you look at 4 more or 2 more or even 5 more, there are many possibilities.
So what we have done so far, when people talk about the standard model Higgs, which isn't necessarily the right wording to use, but they've assumed the simplest solution for the problem of the mass of the fundamental.
This is the most simple solution, the most minimal solution. Yeah. And we've seen very often in particle physics that nature did not realize the most minimal solution. It starts with with our matter, which is made out of 2 quarks, 1 electron, and then you can add a neutrino if you want. But this is only what we call the first family. There are 2 more families, and originally nobody thought about it because there was no need for that. But nature chose this way, and we have no idea why this is the case.
Yeah. So it's natural that we find this kind of first level first, but there could be more.
Exactly. This is what we've seen several times. Yes.
Yeah. Makes sense.
Absolutely.
Okay, so you mentioned, so you need a very nice segue into this. Why do we need these models? So we've said that there is room for these models in the theoretical space, and they haven't been ruled out by experiment. What sort of advantages could they give us? Could they help us answer some of the big open questions that we have in particle physics?
Yes, absolutely. One of the big open questions is, why is there more matter than antimatter in the universe?
I'm an older LHCb person, so this is very much, in my field. So excellent. Good.
Yes. And there is one mechanism that has been not invented, thought of or found that can create, one starts out with the universe with a Big Bang that is symmetric in matter and antimatter, the same amount. And the question is, why only some matter survived and not the antimatter? And there is a mechanism that can take place in the very early universe, 10 to the minus 16 seconds or even earlier, which is called baryogenesis. And this requires, among other things, it requires a so-called non-thermal equilibrium. I don't want to go into too many technical details. It requires
But it needs the universe to be out of equilibrium. Otherwise, any discrepancy would be immediately corrected, and
yes,
we wouldn't get the
this is correct.
persisting.
This is correct, and this can happen with the help of the Higgs sector. One can see this like this: the Higgs sector or the Higgs field has a potential. Physicists know what a potential is, and we started out in the in the minimum. We always live in the minimum of the potential. This is the state of lowest energy, the minimum of the potential. And it started out to be at the origin where the fields are zero. Yeah. And the potential has, in the beginning of the universe, one thinks of, has a form where, well, this is already where we live now. This is where we live now. But when the universe was created, the potential had a different shape.
Yeah.
It had a shape where no extra minimum existed, but where we have a kind of symmetric shape like this. Yeah. And then the universe cools down, and a second minimum starts to form. And then the question is how we get from the minimum in the center that we see here in the plot, which was originally minimum, get to the new minimum that has formed by cooling down. And there are two ways to have this transition, which is called then a phase transition. When we go from the minimum at the origin to a different minimum, this is a phase transition. And physicists know that there are two types of phase transition, first and second order. And this depends on how the second minimum forms. This can be a smooth rollover. And this is what would happen in the standard model, Higgs sector. Or it can be the case that we have one minimum and then a barrier and the second minimum. And then at some point we tunnel through, a quantum tunneling from one state to the other. And this is the first order phase transition. And this is what we need exactly in order that baryogenesis is active and can create the matter-antimatter symmetry. But this cannot happen in the standard model. This has been calculated, and it's not possible. It would have been possible if the mass of the Higgs boson was below 70 GeV. We know the Higgs that we found is 125, so it can't work in the standard model. And this naturally brings us to extended Higgs sectors, where there are more Higgs bosons, and we can have this quantum tunneling at the very early universe and the strong first order phase transition.
Interesting. So it can answer another question. This question of so just for people out there, for every particle there's a corresponding antiparticle, but in the universe that we see today, we basically only see matter. So
only particles, not antiparticles.
Yes. Exactly right. So it's strange because we believe in the early universe that the universe was created with equal amounts. So where has all the antimatter gone? Potentially, the extended Higgs sector could be a way for answering that question.
Yes, this mechanism is necessary so that this baryogenesis, which requires then some other stuff, but this is one of the requirements that baryogenesis works. And effectively, this creates a very small imbalance between matter and antimatter, and then everything annihilated. All the antimatter particles met their matter particle brother, and they annihilated and went into photons. And this is why we see many, many photons in the universe. And then we are just a little bit of matter that is left.
Exactly.
This is what we think has happened.
So that's one massive question. I've also seen, I think in your piece, Sven, potentially addressing the origin of dark matter. Is this another possibility for extended Higgs sectors?
That is correct. Extended Higgs sectors, when we have more Higgs bosons, one of these Higgs bosons can be the dark matter particle, which is in compliance with all the measurements that we have, meaning the dark matter relic density that has been measured and all the experiments that are performed to search for dark matter. There are these so-called direct detection experiments, usually giant
xenon tanks and things like this.
Tanks with xenon, or now they're constructing with argon, or they build crystals, which are more compact, but this is the other way. And then we hope that the dark matter particle hits one of the atoms and releases a little bit of energy, which is then detected. And there are limits on all these particles, the interaction with the detector. And of course, every model that gives you a dark matter candidate has to be in compliance with these limits.
Of course,
And as I was saying, an extended Higgs sector, a new Higgs boson, so to say, can be a good dark matter candidate that is in agreement with all these limits and also gives us the right amount of dark matter that we've observed in the universe.
It's always good to have theoretical models that answer potentially 2-3 potential open questions.
Absolutely.
Right? This gives us more interest in that as a potential thing that happens in the universe.
I fully agree. Yeah. And if I may say this,
please.
One of my favorite models, although people got a bit tired of it over the last years, is supersymmetry.
Yeah, of course, yeah.
And which solves several of the open questions.
Yeah.
And this model, or the supersymmetric models, naturally require extended Higgs sectors. Yeah, they have at least 5 Higgs bosons or 7 Higgs bosons or so. Yeah, they can't do it with only one. This doesn't work. So this is another way that models from other requirements naturally give you more than one Higgs boson.
Yeah. So it doesn't necessarily mean that this is how nature behaves, but it does. It is a candidate worth looking at to answer multiple open questions in physics.
Yes.
I saw one mention earlier, Sven. I'm not sure if this is appropriate, but potentially an answer for neutrino masses as well, or?
Well, neutrino masses are a bit more complicated. We were saying before that the Higgs mechanism gives mass to all the particles that we see.
Yeah.
And in principle, the Higgs mechanism can also give masses to the neutrinos, but it's not very elegant because there's this huge mass hierarchy between the neutrinos and even then the lightest, next to lightest state, which is the electron.
Yeah.
So one needs some other mechanisms. This can be embedded in Higgs sectors, but usually kind of other mechanisms are thought of. I wouldn't call them extended Higgs sectors necessarily. Yeah. So for me, there's less a connection. But I'm also not so much into neutrino physics. So
that's okay. We'll leave that. We'll leave that one for now. So super. So we've got this possibility that these extended Higgs sectors are still there and they haven't been ruled out. And these models answer a lot of open questions. So they're a very interesting field of theoretical research and experiments that are looking potentially for these resonances that might reveal these extended Higgs sectors. So if these Higgs bosons, these additional Higgs bosons were to exist, why might we not have seen them yet at the LHC? Because people might ask, if they're watching, they might have seen, for example, the very famous Higgs plots that we have. If I can find one now, I know I've got it. They might have seen these very famous Higgs plots where it's quite obvious that we have this bump for a Higgs. Why are we not seeing, one over here and one over here? And why are they missing?
This is a very valid question. And there are two ways or two reasons why we may have missed so far another Higgs boson or one of the many other Higgs bosons. First of all, they could all be heavier. I mean, this plot here stops at 160 GeV, and it could well be that they are at around 500 GeV, 1000 GeV or so, and we just didn't have enough energy in our colliders to produce them. This is one possibility. The other possibility is that they are lighter, and this plot also stops at 100 GeV, as we see here. There could be anything between, in principle, anything between 0 and 125. And that just the coupling of this additional Higgs boson to the standard model particles is small. So we in a collider.
So the peak is going to be much lower for a given amount of data. You're going to have it.
The bump that this would produce would be potentially much lower, and therefore more difficult to detect. Furthermore, at the LHC, the lower you go in energy, the less energy the particles have, and then it's more difficult to see them at the LHC.
Well, you can also see, for people watching, the background is going up and up and up. So I imagine you're getting a lower signal to background ratio as well.
Absolutely. The background is going up, and the particles become, we say, softer, lower in energy that are produced. And then it's more and more difficult to see them in this environment where we are dealing with high energy collisions. It's very difficult for the LHC to go to lower energies, to see something at lower energies. And in fact, there are effectively two channels where the LHC might see something, where they're really actively looking for light Higgs bosons, because the LHC physicists believe that they have a chance there. And one is the decay to 2 photons, that is also seen here in the plot. And the other one is the decay to tau leptons, to tau plus, tau minus. This is one possibility. Exactly. This is the channel that is, whoops, now it disappeared.
Oh, I can go back. That's all right. I can get that.
This is how you could produce a Higgs at the LHC. You start out with 2 gluons from 2 protons. By a top triangle, you produce the Higgs. This is the strongest channel at the LHC because the gluon content of the proton is so large. And then it decays to two photons, which can go again via a top triangle, via a W, or via other charged particles that couple there.
Because people might wonder here, how is the Higgs coupling to a photon that has no mass? Well, it goes through this top triangle first, and then the top.
Yes, and the same is true for the other side, because the gluons also don't have mass.
Exactly, correct. It's the
both same sides. Way of thinking here. Yeah.
Okay, so it could be hiding at higher mass. So is just as we kind of pass as an aside, Sven, would a future circular collider or a muon collider also be good for looking for these extended sectors, perhaps? Would this be something that we might still be looking for into the future?
Yes, people are thinking about the next generation of colliders, and among the community, there's a widespread consensus that it should be in a plus and minus collider. Yeah. And the reason is that in the plus and minus collider can produce the Higgs that we know that exists at 125, can study it very, very well. Yeah. And then there are different concepts on the market, and it's still to be decided if one of them will be built or which one will be built. There are as you mentioned, the circular ones, and there are also linear options. Yeah. And both have their advantages and disadvantages. Yeah? And for light Higgs boson, depending on how it's realized, maybe it doesn't matter which option we have.
I guess you want very, very clean. So lepton would be nice, I guess, to
yes,
have
exactly. This is the reason. Yeah. We have point-like particles that collide. We can tune the energy very nicely, and then we can just produce this new particle and study it in very detail. Whereas at the LHC, we always have these protons, which are composed of many internal particles that collide. You have many collisions at the same time. It's very dirty. Yeah. But with electron-positron, it would be perfect. Yeah. But as I said, it will depend on the nature of this additional Higgs boson, whether we can produce it. The channel that would be used at a plus and minus collider to look for it, the main channel is the plus and minus go to a Z boson, and then the Z radiates the Higgs. Okay. And then this Higgs can be studied. Of course, this assumes that the new Higgs boson has a coupling to the Z. If this coupling for some reason is 0, which in principle could be, then we have to think of other channels. There are other channels that one can look at also at the plus-minus colliders that might require somewhat higher energies. But this is the main channel that one normally has in mind. Yes, and this has also been investigated. If there is a new Higgs boson, what properties can be determined, or to which precision they can be determined at this future machine that we hope to get in, I don't know.
So this is a very active area of research, and the phenomenology that we might be able to see at a new collider is something that people are looking at for these extended Higgs sectors.
Yes, absolutely.
Okay, so experiment hasn't ruled out these sectors. They answer a lot of open questions. Yes. We might not have seen them so far because they could be heavier or they could interact very weakly. And one way we can go looking for them is using Higgs decays to two photons or Higgs decays to tauons. So to tauons, to taus.
Both, you can say both.
So that brings me on to the results that you are intrigued with and which you have studied and produced and written a nice preprint on. So what results do we have so far regarding searches for additional light Higgs bosons and how significant are they? Yes. So this is the work you have kind of done with your collaborators.
With Thomas and Georg. We did these investigations. And there is, as I said, the channel to photons is the one channel that may be most accessible at the LHC or most clean at the LHC. And it started out, the LHC is collecting data and doing analysis, then they collect more data and they do more analysis, etc. This is normal. And at the very beginning, many years back, one of the two big experiments for these searches, the CMS experiment, there's ATLAS and CMS. But CMS saw an axis around 95, 96 GeV. Yeah. And then they refined the analysis, they took more data, and the axis persisted. They did the analysis better and better, and they persisted. And this is seen here in the black line. Yeah. I can walk you through the various lines that we see here if you're interested. But
please,
I'm not
because even I, as a former particle physicist, was like, there's a lot going on here. So
yes, so on the x-axis we have the mass of the particle that we are looking for.
Yeah.
Huh? So going from 80 to 110.
Yeah.
Good. On the y-axis we have what we call the signal strength. This is the cross-section glue going to Higgs times the decay probability, the branching ratio, Higgs to photon, divided by the standard model value.
Okay, so just to back up for people, we have to produce the Higgs, and then it has to decay into the things we want. That is a multiplicative probability. Yes. It's probability
times probability of decay.
Yeah, good. So that's a multiplicative probability. The probability of producing your Higgs times by the probability that then that Higgs goes to gamma gamma. Right. Good.
Yes, exactly.
Okay.
And for simplicity or for better comparison, this is divided by the same value that you get by calculation from a standard model Higgs, where just the mass has been adjusted to be either 80, 85, 90, and so on.
Okay.
Just to have a normalization, to have it easier to analyze.
Right.
So then let's start with the black dashed line.
Okay.
Black dashed line on the left plot. Let's look at the left plot.
Yeah.
The black dashed line is the limit that CMS expected to see in the absence of any new physics.
Okay, so this is baseline. Dashed is baseline that we
dashed is baseline, yeah. So
standard model baseline.
To see.
Yeah.
And then around the black dashed line, there's the green and the yellow area, which are the uncertainties they expect, statistical and systematical uncertainties. Yeah. Good. Now this has to be compared with their actual
data
observation, the data. And the data is the solid black line.
Right.
And one can see the solid black line. As long as the solid black line is within the green and the yellow area,
nobody really cares. Everyone's happy. Yeah, everyone is happy.
Exactly. So, and one can see there is this little bump around 90. This is where the Z boson is located, and you have larger backgrounds, and therefore it's difficult to get rid of this. So this is probably the Z boson. Okay. But then at 95, exact 95.4, one can see that the black line leaves the yellow area.
Yeah.
Yeah. And this indicates that they see more events, more events, I would say more photon pairs that they would expect if there was no Higgs boson.
So just for people who are watching, if you compared that to, the very famous plot, it's not as high significance, but you can see that maybe there is a bump above the background.
Yes.
And that's how we discovered the quote unquote standard model Higgs that people talk about. But we might be seeing something similar here at around 95 GeV.
Yes, exactly. And so this was CMS. Yeah. And then ATLAS, the other big experiment, also released their data. And this is they have the red dashed line. This is their expectation, which is quite close to the CMS black dashed line. Yeah, very good. So the two experiments have the same sensitivity. And their result is the red solid line.
Yes.
And they don't go out of their yellow band. We don't show the yellow band, but they don't go out of their yellow band. But the highest deviation that they see is exactly at the same mass as CMS has also seen their peak, namely 95.4 GeV. And this is what if you would do a naive addition of red and black solid line, in most of the cases they level out. But at 95.4, you see these two peaks.
And this gives people a little bit of confidence that there might be something there, because when we look for the Higgs in the past, you would have seen a smaller bump in CMS and a smaller bump in ATLAS, and then they combine them and they reinforce one another. So
when the Higgs boson discovery was announced, this was the remarkable thing that they saw the same thing at the same mass value at around 125 GeV. And then we knew there must be something. This was the big thing. And maybe let's finish with the left plot and then we come to the right, which is very similar. One can see there is a vertical black line with a dot. Yes, exactly. This black line with a dot. And this is the what we would call the measurement of the production cross-section times the decay probability from CMS. And the dot is the measurement, and then the black lines is the uncertainty.
Yeah.
And the same for ATLAS. This is the red vertical line, dot, and uncertainty. And they are nicely overlapping. And what we did is, well, it would be nice if the experimentalists would do a combination, but they don't like this before they don't have a discovery on their own. Yeah. So then it's up to us theorists to do the same work, but of course much less sophisticated. And then we arrived on the right plot at this cyan bar.
Yeah.
With the dot is our measurement, so to say, with the 1 sigma uncertainty. Yeah. And it looks very nice. And this is 3 sigma away from 0, or 3.1 sigma away from 0.
Yeah.
It's not the world, but it's very nice and encouraging, as I said.
But 3 sigma is when people start, okay.
Yeah, exactly. Yeah. I mean, we've seen many 3 sigma things over the years, but as I said, also this channel, the search channel, persisted over 5, 6, 7 years already with new data, and they had many chances to rule it out, to say, no, we don't see anything, and they never said it.
So if there's going to be statistical fluctuations, you might have expected, it's not necessarily the case, but you might have expected it would have gone down and up or gone the other way, exactly. and it hasn't. It's kind of gradually just become more significant, which is what you would expect if, and it might not be, but if there was something there, this is what you would expect. It persists and grows.
This is correct. And I'm not sure whether you want to go there right now, but there's one more thing in the plots that we haven't discussed, which are the orange and the blue points. You want to talk about?
I think we're going to come on to that in a second. What that might be. Yes, but thank you very much. Yeah, you understand what we need to do. Yeah. So just before we go off the mathematics that you've done, so I was talking to Martin Bauer over in Durham, and he very politely he called these these 3 sigma theorist sigmas, which you sort of mentioned. So I have a couple of challenges with the kind of 3 sigmas. So my experience working on LHCb tells me that combining data from different experiments is really, really challenging. So we think about the original Higgs discovery, ATLAS, CMS. This was a gargantuan challenge to combine these statistical and systematic uncertainties. What are the challenges with doing this kind of combination? Because it's kind of easy to do the maths and say it's kind of 3 sigma in theory, but what are the dangers maybe with the dangers
or the challenges are the correlations between the 2 data sets. They may have something in common, and if there's something in common that may lead to fluctuations at the same point, then you would
reinforcing
too much. You would overestimate what you are seeing. And
but I guess this is work. This is where your work would benefit from feed in from ATLAS and CMS to say if there's anything in that region,
but
right?
This is beyond our capabilities. We can't take this into account correctly. So that's really up to the experimentalists to do the job. But I can tell you, when in 2011, before the Higgs discovery, the first bumps appeared. I mean, it was also there. The discovery was announced on 4th of July 2012, but the first data appeared already, I think it was 13th of December 2011. And there was a plot from ATLAS and one from CMS, like these ones here. And they both saw an axis of events around 125 GeV, but they didn't want to make a combination. And there were also people those days, not me, but others, that combined this data, and then you saw a very nice peak at 125. And this was criticized, and probably rightly so, as scientifically not correct. Because the correlations are all neglected. However, when then the real combination appeared, it was not very far from what the theorists had done before. So I don't claim that we do a very precise and optimal job here, but it's the best that one can do with the knowledge and the data that we have.
So you're being cautious, but you're saying this is something that's still worth looking at, and history has shown that looking at these things can be instructive. Not always, but it can be instructive, can be useful.
Yes, absolutely.
Makes sense. So, okay, good. So if these excesses do hold up and they continue to strengthen over the operation of the high luminosity LHC, perhaps, what kinds of models? You gave me the brilliant segue.
Sorry, before we go there, I'd like to mention one more thing.
Please do.
And this is that there is one more experiment that also saw a very interesting axis at more or less the same mass. And I think we always try to take this into account, because here you would say, okay, there are two experiments in this gamma-gamma decay where they see it. But in the LHC tunnel, before the LHC existed, there was a plus-minus collider called LEP. And exactly. And they were also looking for Higgs bosons, of course. And they didn't see anything. They only went up to an energy of 114 GeV, which is below 125. So they couldn't see what has now been discovered. But there's one axis at the level of 2 sigma, more or less at the same mass. Around between, they say 97, 98, but it's a very broad axis because it's a different channel. It's a channel where the Higgs decays to BB bar, not to gamma gamma. It's a different decay channel. And this is what makes it interesting, so that we have more information about this potential new object. We know how it's produced there via the radiation from a Z boson and then decays to BB bar. So these are different couplings that come into the game, the coupling to the Z and the coupling to quarks, or to B quarks. Whereas on the other one, we need the coupling to top quarks to get the decay to photons and the production. And this is what makes it interesting. And the fact that these two axes appeared more or less at the same mass in different channels and completely independent experiments made it very interesting for us to also take into account these old results from LEP, which are from the year 98, 99, 2000.
Sven, that raises another question, Sven. Have there been, obviously at the LHC, you mentioned that things get messy. Have there been any other observations of this potential excess in other decay channels rather than just gamma-gamma?
There is one more indication, but this has to be taken with a grain of salt. And this is exactly the other decay that I was mentioning before, the decay to tau plus, tau minus. And there, also in the production of two gluons, top triangle produce a Higgs, the Higgs decays to tau plus, tau minus. CMS saw an axis at the same mass at the level of 2.5 sigma or so. This looked very interesting, and we also wrote a paper about this. but, and this is the problem, there are other searches by CMS where the Higgs boson is produced in a different way, not from two gluons, but from two quarks. The quarks give you a Z, and then the Z again radiates the Higgs. And this decays to tau tau. Or you start out with a top quark, and then the top radiates the Higgs boson. The coupling of the top to the Higgs is large, and then it gives us a Higgs boson, and the Higgs decays to tau plus, tau minus. And those two channels didn't see any axis. And this 2.5 sigma axis that was seen by CMS in this one channel is in contradiction with data of the other two search channels. And therefore, we are a bit more cautious about the tau-tau decay channel. One can look at it, but it's the weakest of the channels, in my opinion.
So if these excesses hold up and continue to strengthen, which hopefully they do, because we're always looking for beyond standard model physics, what would be the kind of theoretical models that best explain these excesses? Because I know you mentioned there's another thing in this plot, these orange and blue dots. What kind of models could potentially explain these excesses?
When we started out to analyze this a few years back, we asked ourselves the same question. And the easiest idea is we just add one more Higgs boson effectively. But when you look at the coupling structure of this new Higgs boson to fermions and to gauge bosons, you see it doesn't work. It can't give you at the same time the CMS, or the gamma-gamma axis, and the LEP axis. It doesn't work. Also, only the gamma-gamma axis doesn't work. So one Higgs boson alone doesn't work. Then you think we make it more complicated. We add this other 4-component structure, the complex doublet, as we call it. And then these are the so-called 2 Higgs doublet models. We have one Higgs doublet in standard model. We have 2 Higgs doublets. with 5 Higgs bosons, and 1 could be light. Again, we found it can't do the job. It's not flexible enough to accommodate these two excesses together.
Okay.
And then we went one step further and added another one component object, which is called a so-called singlet. Yeah, so we have one doublet from the standard model, another, and one singlet.
Okay.
And this gives us in total 6 Higgs bosons in the model, where one of them can be very light naturally. And we found that this is an ideal candidate to describe the data. And this is what we've done here when these new analysis came out and we did the combination of the data. We took our model and there are variants of this model. I will not go into details, variants about the coupling structure to the...
But these are different, like almost a parameter search, tweaking the parameters of that.
Yeah, well, we scanned the relevant parameter space. We know where to look by now.
Yeah.
And as I said, there are 2 versions of the model. One is resulting in the orange one, and one is resulting in the blue one. You see the label, it's called type 2 and type 4, but let's not go into the details here. Yeah. What is important, that we found many points in the model that naturally fulfill all the constraints that we have from additional Higgs boson searches, from the requirement that Higgs at 125 behaves as the LHC tells us, from other precision data that we have, where also these Higgs bosons have influence. All the points that we see fulfill all these constraints.
Okay, so these models might seem, when people hear, you know, another doublet, another singlet, people might say, this is just going crazy and out of the... But those models are obviously completely constrained within themselves by the observations.
Oh, there's a lot of other data that has to be in agreement with the model predictions.
Yeah.
And since you mentioned it before, this model that we are using also gives you a dark matter candidate. And the points that we see have this dark matter candidate in agreement with all the data. Yeah. But the interplay between the dark matter candidate and the Higgs at 95 is relatively mild. You don't get large connections between the two of them. They are 2 independent parts of the sector that can either give you dark matter or give you the Higgs at 95. But this works out very nicely here.
I just think this is important to get across to people, because I think some people have the kind of popular perception that theorists are just going like, oh, I'll just throw a load of things up in the air and maybe it works. But these models that they're coming up with, theorists, have to be constrained by the experimental data. You can't just make everything up and just say, oh, okay, it gets this constraint, data, but it breaks loads of other, it makes this excess, but it breaks loads of other things. That would not be an appropriate model.
Absolutely. I could talk half an hour easily about all the various constraints that we're taking into account, but this goes beyond, I think, what we have in mind here. But just to mention, as I said, the Higgs bosons all have to be in agreement with these searches. Yeah. The 125 GeV Higgs boson has to behave correctly. Yeah. Then we have low energy collider data looking into what we call flavor physics, what the LHCb is doing. And there's many data where this additional Higgs bosons play an important role, and it gives you a lot of constraints. The potential, we were talking about the vacuum before. We must live in the correct vacuum, All these additional Higgs bosons give you more vacuum, and we still must live in the correct one. And all this is taken into account in this analysis, So the points that you see are in agreement with all theoretical and all experimental constraints that there are.
Very interesting. So this raises another challenge, Sven. So so you mentioned that there might be 6 now. So where are these other scalars? You managed to explain the excess. You managed to explain the peak at 125.
Yes.
Where are the other excesses in the data? Is this low coupling? Is this that the masses are too high? Maybe where could these other excesses be? If we're saying there's 6, why are we only seeing this extra 1 at 95? Where are the others?
Normally, we assume that the other masses are higher. Yeah. And there is no strict upper bound on the mass scale. One gets restrictions from other requirements.
But the models do allow these other ones to sit higher than the 95.
Yes, easily. In principle, the masses are free parameters. Okay. Maybe I make one more connection here. to one of my favorite models. We also analyzed the same thing in a different article in a supersymmetric model. Where we also have the Higgs at 95 and then the other one's higher. And there we have many more restrictions. And in those models, we could make predictions that at the high luminosity run at the LHC or so, depending on what we assume, what has been seen, we should see something else as well. The Higgs sector in supersymmetric models is much more restricted, has much less freedom than in these models where we only assume more Higgses. And there the predictions are clearer, I would say. But in principle, one can just put the masses higher and hope that they are in the range that the LHC will reach, or in the range of future E plus minus colliders. But as I said, there's no guarantee to see them, unfortunately.
But it's very interesting because people are getting a kind of insight into that interplay between experimentalism and theoretical work. So we start to see this small excess, and then the theorists go away and think about ways that we might be able to explain that away. And it's nice to see this interplay.
It's always, yes, it's very important, the interplay, that we talk to our experimental friends. I mean, in order to understand their data, we have to talk a lot to our CMS and ATLAS friends. And then we got these results out. And also, I think they get intrigued and they think, the question is, where do we put emphasis, where we put the person power to do the next analysis? And if we tell them, look, here it really looks interesting, then they are also more intrigued to refine their analysis and to do it more quickly, or just to put the persons on this right now and not wait another year or so.
No, you've done a really good job. Because I'm naturally skeptical of this. 2-3 sigma, I've seen them disappear a lot, but you've done a very good job of being the salesman for this, Sven. I'm intrigued still. So hopefully,
this is my favorite axis, and it has persisted over the years.
Hopefully, it will continue to do so and only strengthen. So. This isn't the focus, Sven, but just as an aside, I don't know if you've seen the work by, let me see if I can find it now. Yes, by Andreas Krivellon and his collaborators, growing evidence of a Higgs triplet. So this is another potential look into extended Higgs sectors, and they believe to have found an even bigger excess, 4.3 sigma at a mass of 152. What do you make of this?
Yes. I know this work, of course, and we talk to each other, and we are organizing a Higgs workshop, a meeting in September in Spain. And I invited the main authors of this to tell us about their work. So, of course, we are all friends and we discuss these things with each other. And I find it very interesting what they are doing. The ansatz is slightly different. And I tell you what I mean. They are mainly we are using search data for a new state. And in the search data, we saw these bumps. They are using analyses that were done for the Higgs that we've seen at 125 GeV. And as we saw before in the gamma-gamma decay, this started at 100 GeV and went to 160. This is where these plots stopped. And they look at these extended ranges and see whether they see some excesses in these searches. Where, as said, the focus was 125, but then there is data that goes up to 160. And they claim to see something, a special thing at around 151 GeV. And I think it's interesting to look at it. I really hope to talk to them in person at this workshop in September, because I have many questions for them.
I know my experimentalist friends were a little bit. So, I mean, the experimentalists naturally skeptical of this, but because there's a lot of combinations of channels that some don't show in excess, some show.
They combine many different channels to get to what they claim to see.
So then those correlations that you talk about becomes an even bigger problem to kind of disentangle.
I guess so, yes, but I'm also not an expert on this. I guess that this is the case, correct? And I would like to see an experimental combination here. I mean, the group is composed of theorists and experimentalists. So but still what they can do is limited. They can't do a full-fledged experimental combination. And I would really like to see this from ATLAS and CMS, that they do this combination. Then I would like to look into it. The point, well, this is one thing. The other thing is that the decay channels that they see are not, well, they say indications for Higgs triplet. We will not go into details, but they have to construct a very special model to fulfill this, that has these different decay channels there. And for me, it's not natural. The other models that we're looking at are, for me, more natural, more easy, and explain easily these axes without going to any special part of the parameter space. Here, this looks more complicated. Yeah.
So we don't want to go too overly complicated. Okay.
Yes. But if you do a podcast with them, please let me know.
Yeah, and we'll keep an eye on it for sure. We'll definitely keep an eye on it, because if that bump starts growing at 152, we will definitely start getting interested in
Obviously, as you were asking before, where are the other Higgs bosons?
Yeah,
there are models that can explain, of course, both 95 and 151 or so. This is in principle possible, and so if this one is found, it does mean that 95 must go away. They could also live together, and then we would have much more information about the Higgs sector.
Very, very interesting. So we'll keep an eye on those excesses. So as we sort of come to the end, because I know you've got another meeting in about 10 minutes, what are the next steps forward to? You've talked about the persistence of this excess over a long period of time. So is this really a case of us getting more data as well, pushing this up to 4 or 5 sigma if it potentially is there? High luminosity LHC, I guess, is going to help with collecting more data in this.
We don't have to go that far. I mean, these analyses are based on what we call the run-2 data, which was taken 2016, 17, and 18.
So we've got a lot more to look at.
Well, no, this has been analyzed. And now then the LHC took a break of a couple of years and restarted in 22, effectively in 22. And so they take data now 22, 23, 24, 25. And this is called run 3. And I'm convinced that if there's something real and ATLAS and CMS do the full run 3 analysis, we will see something at the 5 sigma level. This should be there. We hope to get some answers even earlier. They don't have to wait until this run 3 is over. They can start, of course, data analysis before with only a subset of what they have. And the question is, well, do they think it's enough data? Do they think it's relevant enough or so? I hope that they are analyzing also data that they have right now, and that we get answers maybe later this year, somewhere next year, about subsets of the data, and that will tell us whether they see again a small bump at the same place or not. And if again a small bump appears, well, one should get more confident in this. On the other hand, I mean, as I was saying, this axis has survived all the data steps in data taking. If at some point the experiments see here we don't see anything in the data at all, then I would also be much more skeptical and I don't know, lose interest or look at something else. But we will see. We are physicists and we have to take the data as it comes, and nature will tell us the truth in the end.
Good. It's good. It's good that, like, I'm glad you didn't say, we're going to have to wait, until the end of the run of the LHC to work out.
No, this is 15 years to go. No, this is not the case. I'm pretty sure that within 3-4 years we will know much more.
Very, very interesting. Good. So watch this space, because we could be seeing something very interesting very, very soon. So, Sven, final question before I let you go, because I know you got a meeting coming up. So, bottom line this for people watching. Why are these small bumps in these esoteric plots for some people? Why are they so exciting? And why should we be continuing to investigate these potential extended Higgs sectors? But give us a 1 minute, 2 minute, why should people care about this? Bottom line it for us. This
is the most basic question of nature, Where do we come from? What are we made of? What are the most fundamental building blocks of nature, and how do they interact, This is the most fundamental question mankind can ask. And this is what we are after. So it's a kind of intellectual quest that we are after here. Yeah. On the other hand, and this is also very important, every step in this investigation over the last hundreds of years, even, where we always dug deeper and deeper into nature, we learned something. And in the end, also all our technology was based on this, but not immediately. It always takes 50, 100 years or so. All our technology that we are using now is based on science like we are doing now that has been done 15 or 100 years ago. So we don't know what this will bring to us, but it was always the case that this basic science not only gives us more knowledge about the fundamental laws of nature, but will also bring technology forward and has thus an impact on our life. Yeah, this is very important to keep in mind. We do both. We are happy to explore this, and we are confident, knowing from history, that this will benefit our life, of us, of our children in the future.
Yeah, super. Thank you very much, Sven. That's
my pleasure.
A lovely place to leave it. You have been a brilliant salesman for this. I am going to be keeping an eye on this. I hope everyone else is going to be keeping an eye on this. And fingers crossed, because we know we've seen things go up and down. Hopefully this will persist. And if and when it does, we'll get you back and we'll talk about it some more. So
yes,
Sven, thank you so much.
Okay, thanks to you.
I'm going to make sure all of your work, your links are down below in the description. So everyone head over and check out this work. There's a beautiful a beautiful piece on the is it on the CERN website talking about this?
Yes, it's on the CERN website. Yeah, the EP newsletter there. This is
EP newsletter.
Easy accessible piece.
Yes, it is very accessible. Made it very, very easy for me to write questions for today. So that was nice. Rather than going through these dense theory papers, that was very nice of you to do. And head over there and check that out, and check out Sven's other work. I will put it down in the description. Sven, have a fantastic day, and
same to you.
I will talk to you again soon.
I hope so. Okay. Bye-bye.
Take care, buddy. Bye now. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comments section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.